Strategy 3, Reversal of Polarity, Cyclisations, Summary of Strategy. This chapter considers in more depth two strategic points that emerged from the discussion of CX disconnections in Chapter 4 to 6. Reversal of polarity. Synthesis of epoxides and halocarbonyl compounds. In Chapter 6 we needed three types of synthon depending on the di-X relationship in the target molecule. For the 1,3-dix relationship we used just one synthon 2. For the 1,2-dix we used related synthons 5 and 8, and for the 1,1-dix 2 more 11 and 14. The synthons for the 1,3-dix and 1,1-dix relationships could be turned into reagents 3, 12 and 15 simply and Y using the natural electrophilic behavior of the carbonyl group. The synthons 5 and 8 for the 1,2-dix relationship could not be turned into reagents so easily. Reagent 6 does not resemble synthon 5 while synthon 8 looks very unstable and such intermediates cannot be made. We solved those problems by using an epoxide 6 for synthon 5 and an haloketone 9 for 8, two apparently different devices that actually rely on the same principle, one that is the subject of this chapter. It is easy to see with synthon 8, if we simply reverse the polarity to the anion 16 we discover a synthon that again uses the natural reactivity of the carbonyl group as an enyl-17, or enyl-8, in equilibrium with the ketone 18 with bromine in acidic solution gives that haloketone 9 with an electro-ophilic carbon atom in the right place. The epoxide 6 is naturally electrophilic, but where does the epoxide come from? By far the most important method of epoxide synthesis is the treatment of alkenes 19 with proxy acids RCO3H21. Alkenes are naturally nucleophilic too. They react with bromine togivdibromides 20 and with electrophilic peroxy acids 21 to give epoxides. Again, these reactions convert nucleophilic alkenes into electrophilic derivatives. A very popular reagent for epoxidation is MCPBA, metachloroperbenzoic acid 21, R equals 3-chlorophenyl, but many other compounds are used. The halogenation of ketones. The halogenation of ketones must be carried out in acid solution to avoid polyhalogenation. So the synthesis of reagent 22, used to make derivatives of carboxylic acids in Chapter 6, is simple providing that we notice the directing effects of the two groups on the benzene ring in 23 and disconnect with Friedel-Crafts in mind. The synthesis is very straightforward, no bromination occurs on the ring as would be accepted in the absence of a Lewis acid. Enyls react with bromine without the need of any catalysis. Point 3. The bromination was unambiguous as the ketone could eno one side only. In general the reaction is suitable only for ketones that are symmetrical 4, e.g. 25, bloked on one side 5, e.g. 23 or 27, or which analyze region selectively 6, e.g. 29. Halogenation of acids. There is no ambiguity in the halogenation of acids as they can of course analyze on one side only. Reliable methods are bromination with PCl3 and bromine or red phosphorus and bromine. The acid is converted into the acyl chloride with PCl3 or the acid bromide by PBr3, formed in the reaction mixture from red phosphorus and bromine. Bromohexanoic acid 34 can be made in good yield if the reaction mixture is worked up with water. 7. If the reaction is quenched with an alcohol, only the acyl halide reacts, and this is a simple way to make bromoesters. 38. The alternative product 39 is not formed. Water and alcohols are poor nucleophiles in the SN2 reaction but better with carbonyl groups. Many chloroacids are available commercially, chloroacetic, propanoic, etc. And chloroacetyl chloride 41 is made on a very large scale industrially. 0.8 The chloroamide 40, needed to make some analeptic tetrazoles, is best disconnected as an amide as 41 is cheap. 0.9 It is better to acylate aniline before nitration to prevent oxidation or over-nitration and reduce the RTN of ortho-nitration. Th yield of 45 is after separation from the orthoisomer. 0.10 Notice that in the last step nitrogen, like oxygen, prefers to attack the acyl rather than the alkyl chloride. Cyclisation reactions. Generally intramolecular reactions are easier than intermolecular reactions, entropy being a major factor. If you want to make an acetyl from a ketone, Chapter 6, it is better to use a diol 47 rather than, say, methanol. The equilibrium is in favor of the cyclic acetyl 48 but not in favor of the methyl acetyl 46. Two molecules, one of each, go into 48 but two alcohols and on ketone, go into 46. Entropy is thermodynamic factor, but the rates of cyclisations to form 3, 5, 6, and 7-membered rings are greater than the rates of corresponding bimolecular reactions. This is kinetics but smaller loss of entropy, fewer degrees of freedom lost in the cyclisation, is also a factor. We should not expect a good yield in an acid-catalyzed ether formation from two alcohols. If the reaction worked at all, we should get dinners of each alcohol as well as the mixed ether 51. But if the reaction were a cyclisation of the diol, then things would be very different. The rate of the cyclisation will be much greater, so even this unpromising reaction sold go well. And no regioselectivity problems would arise. If the side chains on nitrogen were different 52, we should still get the same product 53 regardless of which O group were protonated ZND which acted as the nucleophile. The parent compound 54 is morpholine and this unit is present in many drugs such as the analgesic phenodoxin 1155. The necessary diol for such compounds come by TWI1, 2-dix disconnections 56, from the amine RNH2 and 2 molecules of ethylene oxide. Now we want the epoxide to react TWI. So an excess is used and the diol 56 cyclized in acid. 0.12. Choosing cyclisation reaction can make possible syntheses we should certainly reject if a bimolecular reaction were required. The ether disconnection 58b gives a perfectly reasonable diol 59 that swold certainly cyclize as we wish. But making 59 would involve creating an ortho relationship with the unwanted para relationship probably preferred. We should not normally consider the Friedel-Crafts alternative 58A as the intermediate 61 would be unstable. But what that means is that 61 will cyclize rapidly to 58. Indeed, it is difficult to isolate 1361 as it gives 58 even at 35. A dramatic example occurs in the last stage of the professor equals duction of sildenafil 63. The Plyza treatment of male erectile dysfunction, better known as Viagradum. The cyclisation of 62 must involve the attack of the nitrogen atom of one amide on the carbonyl atom of the other. Arrows show first stage. This is an exceptionally difficult reaction. Amides are very poor nucleophiles and very poor electrophiles. Yet this reaction goes in over 90% yield. 0.14. It does so because it is intramolecular. The diamide 62 is heated under reflux for several hours in T-butanol with the base T-buic as catalyst, so it may be that the anion of the nucleophilic ane is involved. Afterwards, dilution with water and neutralization to pH 7.5 with hydrogen chloride gives pure 63. Summary of strategy. In Chapter 1 we gave the bare bones of synthetic strategy. We can now add life to those bones by adding the main points from Chapter 2 to 7. There will be fuller outlines as the book progresses. Analysis. Recognize the functional groups in the target molecule. Disconnect with known reliable reactions in MINT, using FGI as needed to give the right FG. Disconnect. Bonds joining an aromatic ring to the rest of the molecule, whether Rx or Rc, Chapters 2 and 3. Any CX bond, Chapter 4, especially. Bond next to carbonyl groups RCOX, Chapter 4. Using two-group disconnection, Chapter 6. Bonds in saturated rings as cyclisations are so good, Chapter 7. Repeat as needed to reach available starting materials. Synthese. Write out the plan in the forward direction, adding reagents and conditions. Check that a rational order of events has been chosen, Chapter 3. Check that chemoselectivity is favorable, Chapter 5. Use protection if necessary, Chapter 9. Modify the plan from points 2 and 3, and later from unexpected failures or successes in the laboratory. Example, salbutamol. The anti-asthma drug salbutamol 64, better known as GSK's Ventolin, is closely related to adrenaline 65. The extra carbon atom, marked with a black blob in 64, prevent dangerous side effects on the heart, and the T-butyl group makes the drug longer lasting. Salbutamol has 3 hydroxyl groups and an amine, but the only 2-group CX disconnection is of the CN bond 64A, revealing the epoxide 66 as a starting material. This approach is successful, but it involves chemistry we encounter in Chapter 30, so we shall discuss it there. An alternative is FGI back to ketone 67 and hence the bromoketone 68 that can be made from the ketone 69 itself by methods discussed earlier in this chapter. The ketone 69 is clearly made by some sort of Friedel-Crafts acylation, but how are we to make the diol 70? In Chapter 3 we said that a good strategy to make ortho-disubstituted aromatic compounds was to start with an available compound with that relationship already present. Here the obvious candidate is salicylic acid 71. Further consultation of Chapter 3 reveals the synthesis of the related ketone 73 by a Friedel-Crafts style reaction on aspirin 72. As we have 2 reductions, of the acid and the ketone, it makes sense to do them both at the end. The plan is now. Checking for chemoselectivity problems, we might suspect that the amine could be alkylated twice by the very reactive bromoketone 74, so it might be better to protect the nitrogen atom with a benzyl group. This can be removed by catalytic hydrogenation. In the laboratory, it proved better to brominate 73 as neutral rather than acidic solution, so the final scheme becomes: the synthesis is short and high-yielding. Make good use of the strategic points used so far in this book and introduces the subject of the next 2 chapters, amine synthesis and the use of protecting groups.